So today we're looking at the problem, the number of beautiful subsets. This question reads that we're given an array nums of positive integers and a positive integer k. A subset of nums is beautiful if it does not contain two integers with an absolute difference equal to k. So what that means is, if we look at our example, our k is 2. So that means we cannot have a subset where we have, for example, 2 and 4, because 4 minus 2 equals 2, and 2 minus 4 equals negative 2, absolute value equals 2. So we have to find the subsets where no two numbers in that subset have an absolute value that's equal to k. And we want to find the non-empty beautiful subsets that we can make from this array nums. So if you haven't done the subsets problem, I would go back and do that first. That's kind of the foundation for this variation of that problem, and it's definitely good to understand. But if you feel ready, let's look at an example in a little more. So there are several ways to do this problem, but some of those are pretty advanced and kind of out of the scope of what you might see in an interview. For this problem, the constraints are very low. Our n value is less than or equal to 20, and this n represents the length of the array that we're given. So when we see a value this low, that's a good chance, a good indicator that we're going to be doing some sort of brute force algorithm like backtracking. So this algorithm that I'm going to show you is based on backtracking, and the time complexity is 2 to the n. Essentially what this means is that for each of these n elements, we have to make two choices. We have two potential choices to make, so that equals 2 to the n. So let's see exactly how we would derive our solution using backtracking. So we would, for example, start with just an empty collection, right? This represents our starting state, nothing really to do here. So now we're going to iterate through each element of our array, and at each element, we're going to have to make a choice, right? The choice is either to include an element or not include an element. So let's say this is for index 0, right? We can either include 2 or we can not include 2. So let's keep going. Now we have another choice to make. So for each of these, we can either include 4 or not include 4. So you notice when we get to this case, we see that this violates our condition, right? We'll see that 4 minus 2 does equal 2, and we know that our k value is 2, so we cannot possibly proceed any farther from here or have this as one of our valid subsets. So at this point, we would just stop and go back. So the other choice is to not include our 4, so that would just still be a set of just 2. So similarly here, we can make the same choice. We either include 4, so we have just 4 now, or we don't include 4, and we still have this empty collection. So now for our last index 2, we have to make the choice for the element 6. So we can do that here. We'll have 2 to the 6th, and this is valid, right? Because if we subtract these values out, we'll see 2 minus 6 equals negative 4, absolute value equals 4, 6 minus 2 equals 4. So this does not equal our k value, so we can keep this in our array. The other choice is not include 6, so we come down and we get just 2. So similar here, we can go down 4 and 6. But this also is not a valid case because we do 6 minus 4 equals 2, which is our k value. And then for our last decision here, we can either keep 6 or leave our collection empty. So we've basically gone through every possible decision that we can make and generated all the potential valid subsets. We don't generate all the subsets because you see when we hit a invalid case, we immediately stop and just go back. And that's kind of the essence of backtracking. We're going to go until we see a case that we know is invalid, and then we're just going to go back and try something else. So once we get through all of our options, we'll see we actually have 4 valid subsets. So we have 2 and 6, we have 2, we have 6, and then we have, forgot a 4 over here. We also have just our 4. So we'll see after doing all this, we have 4 valid subsets, which is our answer. So this is going to be 2 to the n is going to be our time complexity. And this is because, as you can see, for each element in the array, we are essentially making 2 choices. We can either include that element or we cannot include that element. And if, say, for example, our k was 3 in this case, and we did go through every single combination and never backtracked, we'd actually end with 8 total subsets, right? So the number of subsets that we generate is whatever our n value is, and we raise that 2 to that power. So that would be 2 to 3 is 8. So this is the worst case scenario when our k value does not eliminate any options. We'd have to go through all these iterations of n and generate all the subsets. So that's how this works. Hopefully that made sense. Let's hop over to the code and take a closer look. So the first thing we're going to do here is sort our original nums array. And we're doing this so that we can kind of avoid having to worry about negatives or absolute value. If we're always starting with the smallest elements, we can always just say, okay, I have a bigger element now. Let me check and see if just whatever element I'm looking at minus k is in my array. So we don't have to worry about absolute value. We don't have to worry about handling negatives. It's just very simple. We're always dealing with bigger and bigger numbers. So we can do a simple subtraction operation to make sure that our subset is valid. So we define this recursive function, which just finds the number of subsets. So what we're doing here is, this is our base case where we get to an index that is greater than the length of our numbers, where we've gone through all the numbers already. So what we'll do here is say, if the length of our current subset is greater than 0, we'll return 1. Otherwise, we return 0. And what this is doing for us is checking that if the current subset is not empty. So we'll just do that here. And then if we don't return from that, we set up an answer variable with similar logic. So if our current subset is not empty, we want to count this subset potentially as part of our answer. Otherwise, we start with 0. So now we're going to iterate through all the numbers from our starting index to the end of the array. And what we're doing here is doing a check and saying, so if the current number I'm looking at minus k is in the subset that we have at this point, we just continue past, because this means that if we add this number, every subset after this would become invalid. So we don't even want to consider this number. We just move on and go to the next iteration. Then what we do is we're going to add this number into our current subset. And then what we're going to do is recursively call our function with the next I value and try to generate all the possible subsets from there. Then at the end, this is where we kind of reverse our backtracking. We're going to pop that number off of our current subset so that we can add the next number and kind of iterate through all those options. Then at the end, we would just return our answer. And here we're just calling that recursive function. So let's submit and make sure that this works. And it does work. So this is just the backtracking solution to this. There are more optimized dynamic programming solutions, but those are much more complicated. Maybe in a future video, we'll go over those. But for the sake of an interview, this solution should be totally fine. So hopefully this made sense, and thank you for watching.